This study presents an experimental and theoretical investigation of the high-field phase diagram of the chiral-lattice antiferromagnet senior TiO, multivalen Tcu4 PO414, employing ultrasound, dielectric, and magnetocaloric effect measurements complemented by cluster meanfield theory. The experimental BT phase diagram reveals two new phase transitions at high fields, attributed to strong magneto-elastic coupling and the chiral-twist effect of multivalen Tcu4012 cupola units. Theoretical calculations based on the cluster meanfield approach are in good agreement with the experimental results, suggesting that SRTC-PO is a unique quasi-wo-dimensional spin system with competing exchange interactions and chirality, leading to a rich phase diagram. The authors also provide a theoretical and experimental analysis of the magnetic properties of SRTC-PO, focusing on its magnetic phase diagram and the spin lattice coupling. The effective spin model for the Cu2 plus cations includes four dominant antiferromagnetic exchange interactions, a Dzhalichinskiy-Moria interaction, and a Zeeman coupling. The Hamiltonian is solved using the cluster meanfield (CMF) theory, which accounts for quantum fluctuations within each cupola and uses meanfield approximation for weaker intercupola interactions. The temperature dependence of the elastic constants at zero field shows anomalies at the ordering temperature, Tn equals 6.3 K, indicating long-range magnetic ordering. The C66 mode exhibits the largest softening, reflecting strong spin lattice coupling with the AB plane shear strain. The other acoustic modes show weaker elastic anomalies, consistent with two-dimensional spin systems where in-plane strains generally exhibit larger spin lattice coupling than out-of-plane strains. The C66 mode at zero field also displays a broad minimum at around 5 K, which gradually disappears with an applied magnetic field. This anomaly is linked to a hump in the specific heat divided by temperature, observed around 5.5 K. Suggesting a possible role of magnetic domains. The authors discuss the potential impact of antiferroquadrupolar magnetic order and domain walls on the observed elastic anomalies, particularly in the context of similar phenomena in other materials like Cu4 and alpha-Nav205. The magnetic order in SRTC-PO is characterized by antiferroquadrupolar type QX2Y2. Where magnetic quadrupoles align in a ferroic manner within the two-dimensional magnetic layer but antiferroically along the axis. The existence of two domains with opposite magnetic quadrupoles could contribute to the observed anomalies in the elastic constants and specific heat. Here is a combined summary of the 4 pages. The research investigates the magnetic field dependence of acoustic properties and the magnetocaloric effect, MCE, in a frustrated magnet, focusing on magnetic field-induced phase transitions and their corresponding elastic and dielectric anomalies. Acoustic properties exhibit discontinuities and hysteresis loops in elastic constants, C66, C11, and C44, for magnetic fields along the 001, 100, and 110 axes, attributed to field-induced phase transitions. The C66 mode shows a complex hysteresis loop, indicating strong in-plane spin-strain correlations. Acoustic attenuation becomes minimal at fields between B001, C1 and B001, C2, suggesting a thermodynamically stable phase. The dielectric constant, epsilon 100, exhibits broad peak structures and hysteresis for magnetic fields along the 001 and 100 axes, respectively, attributed to the exchange striction mechanism. The MCE data reveal reversible and irreversible temperature changes depending on the initial temperature, T0, and magnetic field direction. Theoretical phase diagrams are presented for a chiral twist angle of phi equals 1 degree, showing that all phases seen for phi equals 0 degrees are also stable for phi equals 1 degree. The study provides a comprehensive understanding of the interplay between magnetic fields, acoustic properties, and the MCE in frustrated magnets, highlighting the importance of considering the chiral twist angle in theoretical models. Theoretical and experimental results on the entropy landscape and elastic anomalies under different magnetic field directions are presented. Entropy calculations and MCE results agree well with theoretical predictions for B parallel 100 and B parallel 110, while a discrepancy is observed for B parallel 001. Elastic constants calculations agree quantitatively with experimental ultrasound results for B parallel 100 and B parallel 110, but show discrepancies for B parallel 001. The research highlights the importance of considering magneto-elastic coupling and the need for refined exchange parameters in the theoretical model for better agreement with experimental results. In the research paper, the authors delve into the high-field magnetic properties of SRTC-PO using ultrasound, dielectric, and magnetocaloric effect measurements. They discover new phase boundaries at B 001, C2 and B 100, C2, which were previously undetected by magnetization measurements. Theoretical calculations employing the cluster mean field (CMF) method are used to understand the origin of these phases. By considering the chiral-twist effect of the cupolas, the BT phase diagram is reasonably well reproduced for three magnetic field directions. The assignments of the field-induced phases are carefully done by comparing the entropy and elastic response obtained by experiments and calculations. The authors propose that the phase between B 001, C1b 001, C2 is the phase 3 predicted by the CMF theory, based on the drastic response of the C66 mode. The reasonable agreement between experiment and theory indicates that the CMF theory well captures the nature of this quantum spin system, where competing exchange interactions and chirality play an important role in the emergence of the rich phase diagram. The paper discusses the stability of the high-field phase in SRTC-PO under various magnetic field orientations and temperatures. Changes in the twist angle significantly influence stability, emphasizing the importance of precise control. The authors present a range of spin configurations obtained using the CMF theory, including the chiral-twist effect, to demonstrate the complex magnetic behavior. These configurations are shown in Figure 11, featuring various field and temperature parameters. The study emphasizes the importance of considering both the magnetic field orientation and temperature to understand the stability of the high-field phase. The paper concludes by highlighting the need for further research into the magnetic properties of SRTC-PO and related materials.